If you follow AI, you know things are moving incredibly fast. Breakthroughs seem to happen, well, almost constantly. But have you ever thought about what actually limits that speed? It's kind of a paradox, isn't it?
Mm.
AI itself is, accelerating like crazy. But the research behind it, designing these systems,
Yeah.
that still seems tied to, well, us, human brain power.
It's a real bottleneck, like this super fast highway for AI progress, but the entrance ramp is still pretty narrow.
Exactly. So today we're diving deep into something aiming right at that bottleneck. It's called ASI-Arch.
Artificial Superintelligence for AI research.
Right. And this isn't just about tweaking existing designs. It's about AI actually autonomously coming up with new AI architectures. Our mission here is to unpack how it works, what it discovered, and what this sort of AlphaGo moment for AI design really means based on the research itself.
Yeah, our main source is this paper, AlphaGo Moment for Model Architecture Discovery. It lays out the ASI-Arch system, its findings, all very empirical. And they used a lot of computation to get these results. It wasn't a small test run.
Okay, so let's talk more about that core paradox the paper highlights.
Yeah.
AI capabilities zoom ahead, but AI research itself is linear, still paced by humans.
That's the argument. While AI compute scales exponentially, the human-driven design process doesn't. So you hit this point where it's not compute power holding things back anymore. It's human research bandwidth, the sheer ability to think up and test new ideas.
Is it really that bottleneck, though, or are we just seeing the limits of current human approaches in this specific area?
Well, the paper argues it's becoming a critical challenge. Every big leap forward, historically, needed humans to conceive, design, test, refine. It's painstaking work. And that human-centric cycle just can't really keep up with the potential speed AI could develop at. This is what drives the vision for ASI-4AI, Artificial Superintelligence for AI research.
Okay.
Systems that can do their own science, basically. Design the next generation of models themselves. And neural architecture discovery, that's seen as a key area for this, because those big shifts like CNNs, then transformers, they all came from new architectures.
Right. They're fundamental.
They really are.
So how does ASI-Arch differ from, say, neural architecture search, NAS? Because NAS automates some things, right?
It does, but NAS operates within limits. It searches a space of possibilities that humans have defined beforehand. It's more like a super optimizer picking the best options from a menu we gave it.
Okay.
ASI-Arch is framed as a different beast entirely. A paradigm shift, the paper calls it. It's moving towards automated innovation.
So the AI is actually hypothesizing new architectural ideas, not just selecting blocks.
That's the core idea. It acts more like a researcher itself.
Interesting. So how does it actually work? What's under the hood?
Well, the ASI-Arch framework is designed as this fully autonomous closed-loop system. It's modular, 3 core roles working together in this continuous evolutionary cycle. Proposing, testing, learning, proposing again, all without a human needing to step in during that loop.
Okay, let's break down those 3 roles. You've got the researcher.
Yep. The researcher is like the creative engine. It proposes the new architectures, it draws on historical data, past experiments, even distilled human knowledge from papers.
Like an AI architect using a library.
Sort of, yeah. Then comes the engineer.
Okay.
The engineer takes those blueprints, turns them into actual code, trains the models, and runs the tests. It's the empirical validation step.
Right, seeing if the idea actually works in practice.
And finally, the analyst. This module takes all the results from the engineer.
The successes and failures.
Both. It synthesizes those results, extracts insights, and feeds that learning back into the system, enriching it with knowledge from a cognition module too. It completes the loop.
So what tells the system if a design is actually good? How does it judge success?
Oh, that's the fitness function. It's key. It's not just about one metric.
Yeah.
It's composite. 1/3 is about improving the loss compared to baseline models. Another third is about improving benchmark scores. And they use this sigmoid transformation here, which is clever. It amplifies even small improvements, making them count more.
So tiny gains still get rewarded significantly.
Right. And the final third, that comes from an LLM judge. A separate large language model evaluates the quality of the architecture itself.
How innovative is it? Is the structure sound? Does it train well? Things like that.
Exactly. It's a qualitative check by an AI expert, essentially. This whole setup tries to prevent reward hacking.
You mean the AI finding some weird trick to boost scores without actually creating a good, useful design?
Yeah. The LLM judge helps ensure the designs are genuinely innovative and well-formed, not just exploiting a metric.
Okay. And you mentioned the engineer tests things. What happens when an architecture just fails, breaks during training? Does it just get thrown out?
No, and this is quite sophisticated. It doesn't just discard failures. ASI-Arch actually captures the error logs.
Okay.
Then it tasks the agent, the AI itself, to analyze why it failed and revise its own code.
So it debugs itself.
Effectively, yes. It keeps trying until the training succeeds, learning from its mistakes. This way, promising ideas aren't just lost because of an initial bug.
That's impressive. But does it ever get stuck fixing bugs forever?
They thought about that. There's an automated quality assurance system running alongside. It monitors the logs. If a run is taking way too long, like 2 or 3 times longer than expected, or if the loss looks weirdly low, often a sign of a deeper bug, it terminates the run.
Ah, so it cuts its losses on runs that seem fundamentally broken or just wildly inefficient.
Right, saves compute resources and keeps the whole discovery process moving faster by pruning those dead ends.
Okay, so it learns from its own mistakes. Where does the initial spark come from? The ideas it starts with is all built on human knowledge.
It uses 2 main knowledge sources. First, the cognition base. This is distilled human expertise. They processed almost 100 key papers on linear attention, extracting the core ideas, the scenario, the algorithm, the context into a structured format.
So a foundation of human research.
Definitely. But the second source is contextual analysis. This is dynamic. It's insights generated from the system's own history of experiments.
Learning from what it's already tried.
Exactly. It looks at parent designs, sibling designs, and its architectural family tree. Basically comparing slightly different versions to see what worked and why. It's like doing its own mini experiments, its own ablation studies, constantly.
So human knowledge plus self-generated knowledge. That makes sense.
It's that combination that fuels the design process.
Okay, now the burning question. With all this setup, the loop, the self-correction, the knowledge bases, what did ASI-Arch actually discover? The paper mentions, what, 1,773 experiments? Over 20,000 GPU hours? That's a serious amount of searching.
It is, and the headline result is the discovery of 106 innovative state-of-the-art linear attention architectures.
106 new SOTA architectures.
Yes, and these aren't just theoretical. They're available in a public model gallery. You can actually see them.
Wow. And the paper calls this an AlphaGo moment in design. That's a strong claim. Like, move 37 and go.
That's the parallel they draw. Just like AlphaGo made moves humans hadn't conceived of, these AI-discovered architectures show emergent design principles. They systematically outperform the human design baseline, sure, but more importantly, they reveal new ways to build these architectures, paths we hadn't thought of.
So it's not just better, it's different. It's teaching us new design philosophies.
That seems to be the implication within the research, yes. It's illuminating new possibilities.
And this leads to another huge finding, a scaling law for scientific discovery itself.
This is potentially massive. They found a strong linear relationship plotted on a graph between the amount of computing time used and the number of new state-of-the-art architectures discovered.
Wait, so you put in more compute hours, you reliably get more breakthroughs out.
That's what the data suggests for this specific domain. It implies that architectural discovery, at least here, can be computationally scaled. Think about that. It shifts research progress from being limited by human ingenuity cycles to being potentially scalable with compute resources. It's, well, a potential game changer for how research could be done.
That is huge. Yeah. And these discoveries weren't just on small models, they validated them.
Right. They use a 2-stage process, explore promising ideas on smaller models first, then rigorously test the best candidates on larger models, and the top models, ASI-Arch, found outperform established human baselines, things like DeltaNet, gated DeltaNet, Mamba2 on standard benchmarks, so the performance holds up.
Okay. And when you look at how the AI searched, did it just get better over time?
Yeah, the analysis shows that. The average fitness score, that combined metric, shoots up quickly at first, then levels off a bit. But the raw benchmark scores keep improving steadily, and the raw loss keeps going down consistently. It clearly learns to generate better and better architectures as it runs.
Does it achieve this by just making models bigger and bigger? Is it just stacking components?
That's a good question, and they looked into it. They analyzed the parameter counts of the models it generated. After an initial exploration phase, the complexity actually stabilized. Most of the successful models landed in the 400 to 600 million parameter range.
So it's not just brute forcing performance with size.
Doesn't seem like it. The gains appear to come from smarter architectures, not just bigger ones. It found better designs within a reasonable size range.
What kinds of building blocks did it prefer? Did it invent totally new components or reuse existing ones?
It showed a definite preference for established, proven components, things like gating mechanisms, convolutions, components known to work well.
Okay.
But here's a fascinating insight. When you look just at the top performing models, that model gallery,
The 106 SOTA ones.
yes, the usual long-tailed distribution of components where you have lots of rarely used parts, it kind of disappears.
Yeah.
Meaning the best models converged on a core set of highly effective, validated techniques. It's like the AI honed in on what really works best, similar to how human engineers refine best practices over time. It suggests a mature design strategy emerging.
So it's learning, it's refining.
Hmm.
But where do the best ideas ultimately come from? Is it mostly recycling human knowledge from the cognition base?
Hmm.
Or is it generating novelty from its own analysis phase?
Oh.
Or just random inspiration?
They analyzed this specifically.
Mhm.
Across all the architectures generated, yes, a lot of the initial ideas trace back to the human knowledge in the cognition base.
Okay, building on our shoulders.
Initially, yes. But, and this is key when you look only at the top performing models, the ones in the gallery,
Yeah.
the proportion of design elements attributed to the system's own analysis phase goes up significantly.
So to get to the really breakthrough stuff, the AI had to learn from its own experiments, summarize those findings, and discover things beyond just what it read in the papers.
That's what the data strongly suggests. True excellence seems to require that self-discovery loop, exploration, analysis, synthesis. It needs to build on its own experience to reach the highest levels.
That makes a lot of sense. Can you give us a flavor of some of these specific AI-designed architectures? What makes them innovative?
Sure, the paper details several. For example, Pathgate FusionNet. It uses this clever two-stage router system to balance local details and global context.
Okay.
Then there's Content Sharp Router. It has a gate that adjusts how sharply it focuses based on the actual content it's processing, more dynamic.
Interesting.
Fusion-gated FRNet tackles a common limitation in gating mechanisms. It uses parallel sigmoid gates, which avoids the typical zero-sum trade-off you get with softmax,
Right.
allowing multiple pathways to be strongly activated simultaneously.
Breaking a common constraint.
Exactly. HigherGateNet introduces learnable floors for information pathways, preventing important routes from collapsing or being ignored during training.
Keeping critical information flowing.
And Atom Multipath GateNet uses a unified, balanced, sparse gate that allows really fine-grained control over multiple information paths right down to the individual token level. Very precise routing.
These sound like genuinely novel approaches, not just recombining old blocks in obvious ways.
That's the point the research makes. These innovations demonstrate performance advantages over the baselines, showcasing what autonomous design can achieve.
Okay, so let's try and wrap this up. At its core, ASI-Arch feels like a really solid proof of concept for this idea of artificial superintelligence for AI research. An AI system that can genuinely explore a complex design space and discover novel, top-tier architectures entirely on its own.
I think that's fair. And the research reinforces that potentially transformative insight that architectural breakthroughs, at least in this context, might now be computationally scalable. It shifts how we might think about AI progress from being fundamentally limited by human research cycles to potentially being accelerated by compute power in a more predictable way. That really changes the landscape.
It really does. It makes you wonder. When the process of scientific discovery itself becomes something we can scale computationally, like ASI-Arch demonstrates, what happens next? What new kinds of AI, what new scientific frontiers might be unlocked when AI isn't just building on our ideas, but truly starts building on its own? Something to think about.